Alright, so in this last video for the chapter, we're going to talk about exponential and logarithmic equations. Now, we can compute values like log base 2 of 8 in our heads because it's the same thing as solving the equation 2 to the x equals 8, and ultimately this is pretty easy to deduce. But what about something like log base 2 of 7? At this point, finding out the value of x that makes 2 to the x equal to 7 in our heads is essentially impossible. This is the kind of thing that you need a computer for. We talked about using the change of base formula, but the easiest thing to do is get your hands on a calculator that can accept multiple logs of pretty much any base that you want. And some calculators or softwares actually have you put two arguments into a log function. But truthfully, this can vary depending on what kind of calculator that you're using. The easiest way to tell which version that you have, if you do have a log function that takes as input two arguments, type in the values log of 2, 8. If you get the value of 3, then your calculator is set to take log, where the first argument is your base, and the second argument is your input. But if you get the value of 1/3, then you have it the other way around. So the point is that if you got a calculator that does log functions like this, it's easy to tell which one you're in just by doing a test value and examining the answer. But part of the point that I'm making here is that sometimes you need computer help to figure out the values of certain logs. Although our answers don't typically need to go this far. Our answers involving things like log base 2 to the 7th or natural log of 5 will typically just remain in this form. We won't require the decimal values, but it's at least good to know how to acquire them, and that's what this first slide is talking about. But the biggest thing here is that I want to get used to the fact that we're going to have expressions like log base 2 of 7 or ln of 5 showing up in our final answers. So let's begin with some motivation in terms of our equation solving discussions. We know how to handle equations like 2 to the x equals to 8 or 4 to the x minus 1 equals to 2, because we can use the strategy of making the bases match and find our solutions that way. But what happens if I have the equation 2 to the x plus 3 equals to 5? Well, now I'm in a different situation because I have no idea what power I can take 2 to get 5 as an answer. So what do we need to do about this? We're going to use a new strategy known as taking the log of both sides. Recall that we have the cancellation law, log base a of a to the x equals to x. In other words, if I have a log outside and an exponential inside with matching bases, then I just get to bring along the exponent that was there. So let's solve the equation 2 to the x plus 3 equals to 5. The left-hand side has a base of 2. So I'm going to use the log base 2 function, and I'm going to take the log base 2 of both sides of this equation. So this would look like log base 2 of 2 to the x plus 3 equals log base 2 of 5. Because on the left-hand side, that log base 2 and exponential with the base of 2 are going to cancel each other out. And this is just going to give me x plus 3 equals log base 2 of 5. And I've got no variables inside that term, so it's just going to be some constant. At this point, I just have a linear equation and I can solve for x by subtracting a 3 from both sides. And this is going to give me the solution to our equation, x equals to log base 2 of 5 minus 3. Now, you could throw all this into a calculator and get an actual numeric value, but that's really not necessary. Typically, this form of our solution is going to be the preferred form, the kind that has logs with bases and numbers, and some other subtractions or additions that might be taking place. That's why I said in the previous slide, it's good to get used to seeing terms like this. It's good to know also how to compute them if we need to, but generally this is the kind of thing that we want, especially in Hawks. Alright, let's get some more practice with this. We're going to solve the equation for x, e to the 15 minus 3 minus 28 is equal to 0. The first thing I'm going to do is rearrange it so that I have my exponential on the left-hand side and my number on the right-hand side. I want to set this up so that I can take the log base e of both sides, or the natural log function, so that that exponential on the left gives me a nice cancellation. So we'll go ahead and take the natural log of both sides to get natural log of e to the 15 minus 3x equals natural log of 28. We'll let the cancellation follow through to get 15 minus 3x equals natural log of 28. And like before, all I have is a linear equation in one variable, so solving for x will give me the final solution of 15 minus ln of 28 divided by 3. For our next example, let's look at 2 to the 4y minus 2 plus 10 equals to 7, and let's solve for y. Let's go ahead and subtract that 10 from both sides so that we can get a nice rearrangement of terms. Just like in the first example, I tried to isolate the exponential term on the left-hand side and put all my constants on the right-hand side. But since I have an exponential term with a base of 2, I will take the log base 2 of both sides. However, the right-hand side of negative 3 prevents us from doing that. I know that I can't take the log of anything negative, so it turns out this equation will have no real solutions. Whenever I have an exponential term on the left-hand side set equal to a negative term on the right-hand side, I can automatically say we have no real solutions. Now let's look at another example, which has two exponential terms, both with a different base. 2 to the x plus 3 equals to 5 to the x minus 1. In previous problems, when I only had one exponential term, it was clear what log I should take of both sides. Thankfully, this does not pose much of a dilemma. All I have to do is just choose which log I want to take, and it really doesn't matter what I pick. So I'm going to choose to take the log base 2 of both sides. When I do that and follow through the cancellation, I'll end up with x plus 3 equals to log base 2 of 5 to the x minus 1. So clearly the cancellation did not take place on the right-hand side, but that's okay because now I can use the power rule to bring that exponent of x minus 1 down and out front. This will give us the equation x plus 3 equals to x minus 1 times log base 2 of 5. Now that log base 2 of 5 is just going to be some constant, so I can distribute it across those parentheses and then get x plus 2 equals to log base 2 of 5 times x minus log base 2 of 5. Since that log base 2 of 5 term is just a constant, I have no variables in it, it just moves around like any other number. So even though notationally it doesn't look as nice, it moves around as though it were like a 3 or a 6 or something. And that's really good news for us because now I have a linear equation in one variable, so all I have to do is rearrange things so I can isolate x and then solve for x. In this case, I'm going to bring all terms with an x to the left-hand side and put all constants on the right-hand side. I'm going to factor out an x, divide both sides by that quantity, and get a final answer of x equals to negative log base 2 of 5 minus 3 divided by 1 minus log base 2 of 5. So it's not a very elegant answer, but that's just sort of a consequence of having a problem like this one. Since I have quite a big problem with multiple exponential terms, it's likely that I'm going to get terms that end up being a little bit gross like this one is. But the punchline is that I could have chosen any log at the very beginning of the problem that I wanted. I could choose log base 2 or log base 5 to start off with. As an exercise, I encourage you to try this problem by taking log base 5 of both sides. Once you've done that, I want you to compare the numeric or decimal answer for the one we've gotten in this slide to the solution that you get and verify that you actually get the same number. The last technique that we'll see for solving exponential equations is the idea of exponentiating both sides. Recall that we had this other cancellation law, a raised to the log base a of x is equal to x itself. And we're going to use this to solve the equation natural log of 2x plus 3 equals to 5. The ln function, of course, is the log function with a base of e, so we are going to exponentiate or lift both sides by e. This is going to give us e raised to the natural log of 2x plus 3 equals e to the 5. And we do this because we can see that on the left-hand side, our exponential and logarithmic terms cancel each other out for having common bases. This is going to give us the equation 2x plus 3 is equal to e to the 5. And now what is e to the 5? It's just some constant. It's something that you can plug into your calculator if you want, but this is the preferred form. So right now, again, I have a linear equation in one variable, so all I need to do is solve for x. By subtracting a 3 and dividing by 2, I'll get that x is equal to e to the 5 minus 3 divided by 2, and we're done. For our last example, we are going to solve the equation log base 5 of x equals log base 5 of 2x plus 3 minus log base 5 of 2x minus 3. Now obviously this is a lot, so the first thing that we're going to do is pay attention to our right-hand side being a difference. We can use the quotient rule to compress this to the equation log base 5 of x equals log base 5 of 2x plus 3 divided by 2x minus 3. Since I have a common base of 5, I'm going to exponentiate or lift both sides by the exponent of 5. This will give us a nice cancellation all through, which will give me the equation x equals 2x plus 3 divided by 2x minus 3. And it turns out all I have here is a rational equation. So using our methods from chapter 3, we can solve this to get solutions of x equals to -1/2 and +3, and we're done.